Newton figured out gravity well enough that we could fly to the moon. Ever wonder if what we know about time is just the tip of the iceberg? Brian Cox's fresh take on time isn't just a theory, it's like a key that might unlock a treasure trove of the universe's secrets, revealing things we never thought possible. So how does his perspective change what we thought we knew about time, and what could that mean for our understanding of reality? Based on Brian Cox's new theory about time and the vast universe around us, there are strange aspects of time and gravity that are fundamental to our existence. Imagine a world where time behaves oddly, speeding up or slowing down. What if gravity isn't what we think? That's where Einstein's theories come in, providing a fresh lens through which to view the universe. Einstein's ideas from the early 1900s form the foundation for understanding how time behaves when things move at incredible speeds. He introduced two major theories, special relativity and general relativity. The special theory, proposed in 1905, revolutionized our understanding of time and space. It states that the laws of physics are the same for everyone who isn't accelerating, regardless of their motion. This leads to fascinating phenomena like time dilation, where time slows down under certain conditions. To grasp time dilation, consider a light clock in a fast-moving spaceship. A beam of light bounces between two mirrors. Since the speed of light is constant for everyone, it appears to travel a longer distance for an outside observer. This means it takes longer for the light to complete its journey, illustrating how time slows down for the moving observer compared to someone standing still. Understanding how things change when moving fast isn't just theoretical. Scientists use machines like the Large Hadron Collider to accelerate particles close to light speed. At these velocities, we must rethink time to get accurate results. Einstein's special relativity has fundamentally altered our view of the universe, particularly regarding time. It reveals that time isn't fixed, it shifts with movement. Special relativity also introduces the concept of length contraction, where moving objects appear shorter in the direction of motion. The famous equation E equals mc squared shows that energy and mass can convert into one another, helping us understand the behavior of tiny particles and nuclear reactions. Special relativity isn't just an abstract idea, it has practical applications. GPS technology relies on it because satellites experience time differently due to their speed. If we didn't account for these time changes, GPS would be inaccurate. Thus, special relativity teaches us that time isn't uniform, it varies based on motion. Einstein's general relativity, introduced in 1915, delves deeper into the relationship between gravity and the structure of the universe. It discards the notion that gravity is merely a force pulling objects together. Instead, it posits that gravity arises from the curvature of space and time. Imagine spacetime as a trampoline. A heavy object like Earth creates a dip, causing nearby objects to roll toward it. This curvature explains how planets orbit the Sun and why Earth's orbit is elliptical rather than circular. A solar eclipse in 1919 provided evidence for general relativity when Sir Arthur Eddington observed starlight bending as it passed near the Sun, confirming Einstein's predictions. Just as motion affects time in special relativity, gravity also influences time. Clocks in strong gravitational fields, like near a black hole, tick more slowly than those in weaker fields. General relativity has profound implications for the universe. Einstein initially included a cosmological constant in his equations, believing the universe was static. When it was discovered that the universe is expanding, he called this a major blunder. The idea of an expanding universe is now a cornerstone of the Big Bang theory, explaining the universe's origins. Another significant concept from general relativity is gravitational waves, ripples in spacetime caused by massive objects moving rapidly. In 2015, scientists at LIGO detected these waves, providing further validation of Einstein's theory. Over time, general relativity has been rigorously tested and consistently holds up, whether through observing starlight bending or detecting gravitational waves. However, questioning gravity and established norms is essential for scientific progress. Some scientists, like Brian Cox, challenge conventional views. One alternative theory is modified Newtonian dynamics, MOND, which suggests gravity behaves differently at low speeds within galaxies, potentially eliminating the need for dark matter. As scientists explore new ideas, they consider concepts like quantum mechanics, which operates under different rules than relativity. While relativity excels at explaining large-scale phenomena, it struggles with the quantum realm, where particles can exist in multiple states simultaneously. This discrepancy presents a challenge for physicists seeking a unified theory of everything. String theory is one promising approach to bridge this gap. It posits that fundamental particles are tiny vibrating strings existing in multiple dimensions beyond our familiar three-dimensional space. This theory suggests the universe may have as many as 10 or 11 dimensions, potentially reconciling the differences between relativity and quantum mechanics. Another area of exploration is quantum gravity, which aims to merge general relativity with quantum mechanics. In classical relativity, gravity is viewed as the curvature of spacetime caused by mass and energy. Quantum gravity proposes that this curvature might arise from quantum fluctuations, revealing a more granular structure of spacetime at the smallest scales. The concept of time itself is also being re-evaluated. While Einstein's relativity introduced the idea that time is not absolute, researchers like Brian Cox suggest there may be even deeper layers to the nature of time. For instance, what if time doesn't flow uniformly everywhere, or if it isn't a linear progression? Some theories propose that time could be cyclical or that its flow might be an illusion created by our perception. Exploring these ideas could have profound implications for our understanding of consciousness, the arrow of time, and the nature of reality itself. Some physicists are investigating the possibility that time is emergent rather than fundamental, arising from the interactions of particles at the quantum level. If time is emergent, it might not serve as a constant backdrop for events but rather as a product of the universe's underlying dynamics. Parallel universes or the multiverse is another intriguing concept. According to some interpretations of quantum mechanics, every possible outcome of an event could occur in a separate parallel universe. This idea, proposed by Hugh Everett in the 1950s, suggests an infinite number of universes, each with its own version of time. Studying these parallel universes could yield new insights into the nature of time and the fundamental structure of reality. Even concepts once considered speculative, like wormholes and time travel, are being taken more seriously. While Einstein's theory allows for the mathematical possibility of wormholes, shortcuts through spacetime that could connect distant parts of the universe, practical challenges remain. Researchers are exploring whether wormholes could enable faster-than-light travel, potentially opening doors to interstellar exploration and time travel. The role of dark matter and dark energy is another significant unknown in understanding time and gravity. These mysterious substances are thought to constitute most of the universe, yet they remain largely undetectable, known only through their gravitational effects. Understanding how dark matter and dark energy interact with spacetime could be crucial for unlocking deeper mysteries of gravity and time. In conclusion, while Einstein's theories of relativity have provided a robust framework for understanding the universe, there is still much to discover. As we explore new ideas in quantum mechanics, string theory, quantum gravity, and the nature of time itself, we are beginning to realize that the universe is far stranger and more complex than we ever imagined. The future of physics holds exciting possibilities that could redefine our understanding of time, space, and reality itself. The journey to uncover these mysteries is far from over.